So backing up to here, since I have this on the screen before I hit the play button, let me just tell you a little bit about what's going on here. So Alan Alda is sitting in this contraption where he can see a computer screen, and he's focusing or staring at the little cross in the middle. This is the fixation point. And while he's staring at that, very briefly, two different shapes appear on the screen on either side. They flash there so quickly he doesn't have time to move his eyes from the fixation point to look at either one of them individually. What this does, it presents one image to half his brain and the other image to the other half of his brain. He had said, or actually he'll probably say it again when I start up, the two halves of his body are controlled by the two separate halves of his cerebrum. Moving muscles on the right side of your body is controlled by neurons on the left side of your brain, and vice versa. The right side of your brain controls muscles on the left side of your body. The visual system works a little bit uniquely in that it's not that the left eyes connect to the right brain and the right eyes connect to the left brain. Instead, it's about the visual field. So if you stare at the fixation point here in the middle, everything on the side of the screen that's got the circle is being processed on the opposite side of your head, opposite side of your brain. And everything from the fixation point over where the square is, that side of the visual field is being processed on the opposite side of the brain. So the left visual field is processed by the right side of the brain, and the right visual field is processed by the left side of the brain. He's going to draw, or what he's attempting to do is draw a circle that he sees on the right side visual field with the left brain using the right hand, which is controlled by the left brain, and vice versa the other way. But his brain's normal in as much as Alan Alda can be called normal, because the two sides of the brain are actually interconnected. And so he's not able to separate this out, which is what they're about to do. What he was about to say right before the thing stopped working. Oh, and I muted it.
Speaking normal, at least all in one piece. The left half of my brain controls the right side of my body, while the right brain controls the left side. Oh, no. But because the two halves are connected, nothing wrong with that. Getting each hand to work independently isn't easy.
Well, we're saying that the fact that Alan's hemispheres are connected, and the motor messages from one are confusing the motor messages of the other.
I was just drawing an upside down duck. But when Joe is given the same task, his two hands operate as if controlled by two separate brains. What's happening is that each half of Joe's brain is given a separate instruction. He's asked to fix his eyes on the cross in the center of the screen. Anything flashed to the right of the cross goes only to his left hemisphere. Things to the left go to his right hemisphere. Because the two don't communicate, each hand does only what its half of the brain sees. Wow. It's really like two different people doing the same.
That's right. That's the idea. Okay, Joe, I want you to keep your hands up.
In an experiment that's now a classic in brain research, Mike Kazaniga over 30 years ago used a similar setup to find out if the two halves of the brain are specialized to do different things.
Sure.
Joe is being flashed a word only to one half of his brain. Words flashed to the right are seen only by his left brain. And Joe can report seeing those words just fine.
Good.
But when a word is flashed to his right brain,
Didn't see that. Okay. So I'm going to ask you
but now watch what happens.
to draw that with your left hand. You're going to be lost. Why don't you try drawing another picture of your that'll help you. Awful. Oh my God.
almost as though somebody has given him a secret communication. That's right. Now he knows that there's a telephone. Up until then, he was blind. Exactly. When Gazzaniga first did this experiment, it instantly proved that the ability to speak resides almost exclusively in the left hemisphere. Not until he sees what his right brain is drawing is Joe able to name it. He said church. But he had to figure out as long as we did. That's really interesting. It's a picture here of somebody communicating almost with another person.
Communication is not occurring inside the head, it's occurring out on a piece of paper.
Yeah.
Wow.
So far, Joe has been seeing only one word. Things get even stranger when he's flashed two words, each to only one half of his brain.
The right hemisphere saw toad.
Yeah. And so his left hand draws a toad.
So there's the toad.
Oh, it's a toad. And this time I was able to guess what was coming. Now I put a little three-legged stool in there. Joe's speaking left brain saw a stool. Saying the word lets the hand that's controlled by his right brain in on the secret. That's great. That's really interesting. And if he had seen that with the corpus callosum intact, he would have drawn a toadstool.
Right.
Yeah, not the toad and the stool.
Right, exactly. I've been doing this for 35 years. Yeah.
And it gets there every time. Yeah.
Okay, so that's the first half. There's a second half there if you're interested in watching that. I also have this video in the video content part of Blackboard. It says girl living with half her brain. This is different from Joe that we were just meeting. Joe has a full brain and it was cut in half. So the two halves of his cerebrum act independently. This girl had, if I remember correctly, encephalitis or something like that as a baby. And so it was fixed by removing half the brain. Now, the fact that it happened when she was that young, her brain kept growing, that half that was left over kept growing and filled up all of the space of her cranial space. So she doesn't have things wired up the way that most other people do, but she does have probably the same amount of nervous tissue in her brain as most other people do. And it's been a while since I've watched this. This is an interview on the Today Show, but if I remember correctly, watching her being interviewed here at 8 or 9 years old, whatever she is, you wouldn't know that she has only half of her brain in there, because since it happened earlier enough, the brain was able to develop and take over the functions that were needed. Okay. This might be the same girl. I'm not sure here. I can't remember, but I do have this video in the Blackboard video content area. There's a few others that address things. Now, I realize I didn't have to explain the sorry, I didn't have to explain the task here because he went on to do that. I can't catch the frame I want. Okay, so he went on to explain it, but that's the idea, that half your brain is responsible for controlling sort of the other half of your body. And with that also receiving sensory input from the other half of the body or other half of the world. So it's not just that he's able to control the muscles to draw with his right hand coming from the left side of his brain, but also the sensory information he gets from touching things with that hand is processed on the other side. But I think this is a really good sort of introduction to the idea of how function gets sort of localized into different parts of the brain. I didn't say anything about language there at the beginning before we started showing this because I wanted to be introduced here. But from this, what Gazzaniga found from more than just working with Joe, but other people with similar issues, is that language function is largely processed in the left side of the brain. Now, when I say largely processed on the left side of the brain, there's actually two variations of what I mean there. One is in about 90% of the population, that's true. Okay? Maybe 95% of the population. So there are some people where language function is either on the other side of the brain, on the right side of the brain instead of the left side, or that language function is distributed equally from one side to the other. But those two cases exist in maybe 5% or so of the population. So largely left side of the brain is responsible for language function. The other thing, which probably wasn't very well understood at the time of this video, and so those statements that are made are actually a little oversimplified, is that there's more to language function than just what is demonstrated here. If Joe was presented with a person who is speaking to him, saying something that sounded very nice and pleasant, but making facial expressions that were very angry and unsettling, the left side of his brain would probably just process the verbal content and say, oh, this is something nice and cheery and whatever. But the right side of his brain would handle the nonverbal side, which would be the emotional content that seems to be portrayed in the facial expressions that might be on there. I took this course in college, which was on animal behavior. It's a biology course, which was kind of interesting. And I really regret I missed one day, and apparently I missed like the best lecture the guy gave all semester, which was he did something like that. He was able to recite some verbal passage that he'd practiced over and over again, but acted out with facial expressions so that it had a completely different emotional content than what was expected. Okay. The rest of the semester, the guy was kind of annoying, but so for whatever reason, I decided not to come in that day. I might have been sick. I might have been skipping. I don't know. But I missed the one lecture that I really, really wish I'd gotten to see, which was basically that. Maybe someday I'll be able to get around to doing that myself as an instructor. I can demonstrate that idea. But all I can suggest is imagine somebody, that's reciting, Itsy Bitsy Spider, okay? But doing it with just facial expressions suggesting, the end of the world, something like that. The verbal content there sounds like a little nursery rhyme. Sounds kind of nice and light and cheery, but the emotional content suggested from the facial expressions might put a completely different spin on it. Okay. I'll have to work on that particular one. Itsy Bitsy Spider and facial expressions, but not a great actor, so not exactly. So it has to be done very well so that you're doing Itsy Bitsy Spider, and you want to smile when you're doing that, and you really got to fight that urge, I suppose. But anyways, so I'd love to be able to show that idea of the emotional content actually being separate from the verbal content, and the right side of the brain seems to be processing more of that sort of thing, which was not at all addressed in what we saw here. This was strictly just recognizing and naming things. What he could, the words that he read and pictures of them. But what was really interesting there at the end when they're talking about, like toadstool, the two words were flashed up on the screen, and the verbal part of his brain, left side of his brain, saw stool. Okay, the nonverbal part saw toad, and so he drew a picture of a toad with the hand that was controlled with the nonverbal side of his brain. Okay. And he said the word stool. And from that, the nonverbal part of his brain was told to draw a stool. Okay. Now, in the basic idea of left side of the brain's about verbal stuff, language stuff, doesn't make sense there. He was able to say the word stool, and from hearing the word stool, the right side of his brain got the necessary information to draw a stool. Okay. And also, he's able to read words with the right side of his brain. more appropriately, what it is probably, and I don't know if this is the best way to say it, is that the conscious perception of language, and to some degree, our conscious perception of ourselves is seated more on the left side of the brain. So he doesn't really experience the right side of his brain, like the side of his brain that saw the word toad. He doesn't have any recollection of that. Earlier on, when it was flashing up just the words like piano and storm, the word that was flashed on the right side, for the right side of his brain, phone, he said, I didn't see a word there. Okay. His internal monologue was, nothing was on the screen. I didn't see anything. Because really, his internal monologue, his sense of self, is based only on what the left side of his brain saw. Okay. And what the right side of his brain saw wasn't processed that way. But it was processing verbal information. It saw the word phone, it knew what a phone was, and it drew a picture of a phone. Or with the toadstool thing, it saw the word toad, it drew a toad. It heard the word stool, it drew a stool. Okay, but it's just really interesting. This is a thing that Alan Alda was really loving there at the end was, somebody with an intact corpus callosum, if they see toadstool on the screen, they're going to draw a mushroom, because that's another name for mushroom. Whereas he saw the two words independently and didn't put them together as a compound word. So he wasn't able to do that. I think I first saw this a long time ago, and I just thought it was really neat. And I like bringing it into the class to talk about things. But it does kind of eat up a lot of time. But I think it's something that's kind of interesting, really showing a little bit of what's going on with function. Okay. Now, going back to what we see on the surface of the brain. So up here, I described the longitudinal fissure and the corpus callosum. The other things that we see on the brain, on the surface of the brain, the wrinkles and folds, those are called gyri and sulci. A gyrus is a fold, and the plural of that is gyri. And a sulcus is a groove. The plural of that is sulci. So we can look at the gyri and sulci, the wrinkles and folds and grooves and all that stuff on the outside surface of the brain, and see landmarks that are consistent across everybody's brain, assuming everybody has the same development. So the girl I pointed out the other video that has half a brain, her brain would not look at all like what we're going to show. It didn't develop in the same way. But by looking at these, we have landmarks that tell us where the different parts of the brain are. Now, the most obvious structure after longitudinal fissure is this groove right here along the side. That's what's called the lateral sulcus. And this separates a lobe of the cerebral cortex called the temporal lobe from the rest of the cerebral cortex. So let me go to this picture here. So here's that lateral sulcus right here. And it kind of outlines this section on the side of the brain. Okay. Now, I say that it separates the temporal lobe from the rest of the cerebral cortex. It's not entirely true. It doesn't separate it here. It just separates the temporal lobe from these two pieces up here. Okay. They are separated from each other by another sulcus that runs right down the center called the central sulcus. The central sulcus separates the frontal lobe from the parietal lobe. Okay. Now, looking at your model, the lateral sulcus is pretty easy to find. Okay, it's just this big thing here on the side. The central sulcus is a little bit trickier to find. Now, I'm going to describe how to find it first, the way that I would tell a medical student how to do this. I used to teach my first real teaching at this level, anatomy and physiology stuff, was teaching a neuroanatomy course for medical students. My graduate school was part of medical school, so I was helping teaching medical students there. So what I would say to them to help them find the central sulcus is you want a sulcus that runs from the longitudinal fissure almost to the lateral sulcus. Okay? It won't quite end at the lateral sulcus, but it will come out of the longitudinal fissure. On either side of it is a gyrus. Okay? So the way you can think about that is you'll have one sulcus down the middle with two gyri on either side. Or there are three sulci that run in parallel, which is really the better way to think about that. Because a gyrus, a fold, is got a groove on either side of it. Okay? So there's going to be a groove right down the middle and then a groove on either side of it. So look for three parallel sulci. One of them, the middle one, should run from the lateral longitudinal fissure to the lateral sulcus. Almost, not quite. The other two might not be complete. And there's a little variation from brain to brain and from model to model exactly where that'll be. But you should see three lines that run down the side of the cerebral cortex here in parallel. Anterior to those three lines, any gyri you see will really be oriented kind of at 90 degrees to them. Okay. And then posterior to that, what little there is also kind of at 90 degrees. Okay. So you should see three lines going down the middle, and any lines posterior or anterior are running kind of at 90 degrees to them. And the middle of those three lines would be the central sulcus. Now, the way that I'd explain that to you looking at these models in front of you is that it's labeled. Now, hopefully it's not labeled the way that I have a model in front of me. Somebody took a pen and drew a line right down the middle there. That's vandalism. Please do not mark these models like that. We could clean that out with some sort of organic solvent. Unfortunately, organic solvents will also erase the paint and possibly eat through the plastic itself. So once somebody's done something like that, it's kind of irreversible. The problem with doing that is, what if whoever did this happened to do it in the wrong sulcus? And everybody would think the wrong sulcus is the lightest. Please do not mark up these things. If you have the hard plastic brain on one side, well, on all of the brain models, on one side there are a bunch of numbers painted on the other side there aren't any numbers. Okay. The idea there is that you have a labeled side and unlabeled side. So on the hard plastic brain, look at the labeled side, and you'll see a 4 painted sort of right on the top there. The 4 is sort of at the top of the gyrus that's posterior to the central sulcus. So if you see the 4 there, go anterior, and the first sulcus you run into is the central sulcus right there. I got to look at the other brain to remind myself what the markings are there. But the other one's actually labeled a little bit more clearly. You will see the number 5 with an arrow and the number 6 and 7. 5 with the arrows pointing at the central sulcus. 6 and 7 are labeling the 2 gyri, the ones that are on either side of the sulcus. And those 2 are important, which I'll talk about later on. But the central sulcus separates those out. So using the lateral sulcus and the central sulcus, looking at the surface of the brain, we see the parietal lobe here, the frontal lobe here, and said that wrong. The temporal lobe here, the frontal lobe here, and the parietal lobe there. There's a 4th lobe, obviously, because there's 4 colors here. There are no landmarks on the external surface here that marks it out. For this drawing here, this line is kind of arbitrarily placed. But it defines the fourth lobe, which is the occipital lobe. Now, what do the names of those 4 lobes correspond with? What's also called temporal, frontal, parietal, and occipital? The bones, right. So the temporal bone is right on top of the temporal lobe. The frontal bone is on top of the frontal lobe. The parietal bones are on top of the parietal lobes, and the occipital bone is on top of the occipital lobe. Okay. So they just correspond to the bone of the cranial space, cranium that is right next to it. Or more appropriately, the bone is named after the lobe right below it. Now, if you look at the medial surface of the brain, you actually will see a landmark between the occipital and temporal lobe. Occipital and parietal lobes. Again, somebody has drawn on this model, but you should see a pretty pronounced sulcus that goes right up the medial surface here. For the soft plastic brain, there doesn't seem to be any real gap between the cerebrum and the cerebellum there. So it sort of is right where the cerebellum goes. And I think on the soft plastic brain, it has a bit more of a curve than it does on here. That has the very unimaginative name of parieto-occipital sulcus, okay, because it separates the parietal from the occipital lobe. Notice that the temporal lobe is not included in that name at all, because the temporal lobe is not visible on this surface. The temporal lobe is here, off to the side. So it's just dividing the parietal from the occipital lobes. That kind of comes over the top of the longitudinal figure right here, but it stops pretty quickly. If you could imagine that line continuing on, that's basically where the occipital lobe's arbitrary line on the picture here on the screen is. So right about there, next to kind of where I'm pointing with the cursor, there'd be the very tip of that parietal occipital sulcus coming over. Or, well, it's labeled right there. So just sort of imagine that coming across here. Imagine a dotted line, and that will kind of show you where it is. Now, those are the landmarks where we can see the major regions of the brain. And each of those lobes we tend to associate with a particular function. Now, when we talked about function before, the divisions of the brain a couple of weeks ago, I introduced the idea of sensory and motor functions. As far as this cerebral cortex is concerned, these 4 lobes are separated basically into motor and sensory functions. The frontal lobe which is pretty massive compared to the other ones there, that's the motor specialized lobe. On the picture, the gyrus that's right next to the central sulcus is labeled the precentral gyrus in the frontal lobe. The neurons in that region of the brain are the ones that tell the muscles to move directly. Now, when I say directly, they aren't connected to the muscles. They are the neurons that connect to the spinal cord, and the spinal cord is connected directly to the muscles. But that's the part of the brain that's responsible for actually initiating movement, voluntary movement. As we move forward, the motor functions get to be more and more, I don't know, what's the word I'm looking for? Removed from the actual movement. Okay. When we get all the way up to the very front of the frontal lobe, what we call the prefrontal lobe, that's what we usually associate with personality, but really in the sense of you are what you do. Okay? The frontal lobe's involved in producing motor functions. The precentral gyrus, the most posterior part of the frontal lobe, is involved in actually making muscles move. As we move forward from that, we get into areas that help plan movements. And then as we move forward from that, we get into areas that help us decide to make movements. And as we move forward for that, we get into areas that help us decide what we should do. And really at the base of personality, who you are is what you do, and what you decide to do is largely centered in that. You've probably heard, as I said, prefrontal lobe a second ago, you probably heard of a prefrontal lobotomy. That's a procedure that hopefully is not performed anymore. Psychiatrically was stopped being performed back in the 60s. But people that had personality disorders would have a prefrontal lobotomy, which would be a knife would be inserted in and cut through some of the white matter of the prefrontal lobe, disconnecting it from the rest of the brain. And what was seen from that often was a severe change in personality. If you're interested in this, there's a movie which, as Hollywood would tend to do, over-exaggerates some issues. But there's a Hollywood actress named Frances Farmer who's rather famous for having suffered prefrontal lobotomy. And in the movie, it's sort of her biopic, but in a Hollywood fashion. There's a lot of sort of exaggeration and embellishment there. But she was a movie actress, I think in the 40s. She's portrayed in the movie as being strong-willed and independent and, a woman. What we want to see from women, thinking by themselves and that sort of thing. But if you're a Hollywood studio boss, women to you are just eye candy to put on the screen. She was not eye candy. She had her own opinions, that sort of thing. So the Hollywood establishment, according to the movie, committed her to a mental institution where she was subjected to various psychiatric interventions. And at the end of the movie, she gets a prefrontal lobotomy. And the last scene in the movie is really pretty striking because she's walking along and there's a character who she's dealt with in the past who, I don't know, hasn't seen her for a little while because she was in the mental institution or whatever, comes up to her and they interact. And Frances, the main character, is, sort of a Stepford wife kind of personality. She's completely docile and complacent, and she's going to now do what everybody wants to do. Now, that's the story. It is embellished a bit. I've read into Frances Farmer a little bit more, and there's some evidence that what the movie portrays is way out of line with what really happened. But Jessica Lange performs as Frances Farmer, and that last scene is just amazing. And I think it's a really good indication of what a prefrontal lobotomy would do. Now, like I said, hopefully those aren't being performed anymore, and they stopped being performed back in the 60s. But that approach is still actually current. Yeah.
So they were trying to make the personality better, the personality disorder better, and actually make it worse?
No, as far as the people that committed her, they made her better. Okay. She stopped being an independent woman, and that's what they wanted. They just wanted her to go ahead and get on set and portray the character that they wanted to. But it profoundly affected who she was as a person, according to the movie. Now, the reason why prefrontal lobotomies fell out of fashion wasn't so much along the lines of, oh my God, we're putting knives in people's heads and cutting their brains out. Instead, it changed because pharmacology came along. So in the 60s, psychoactive drugs became more common. And so if somebody had a personality disorder, you could do a chemical alteration of their personality. Earlier psychoactive drugs might have been almost as irreversible as a prefrontal lobotomy. But nowadays, things like Prozac or whatever do the trick. Frances Farmer, if she was around today, would be prescribed Prozac. That would make her so much happier, right? And complacent and do things that she didn't do. My dad's a psychiatrist, and when I was in college, I followed him, when I was off from college, spring break or whatever, I followed him in his job for 2 days. I wanted to see what things were going on. What psychiatry was like. The first day, I got to see him admit a patient who was manic. Okay? My dad works at a state hospital, or did at the time. And so this guy came in acting like he was on drugs. He was just all over the place. He was talking a mile a minute, and what he was saying was just completely disconnected meaning-wise. He would go off on a tangent this way and that way and just jump from idea to idea, and he would just go a mile a minute. My dad prescribed to him an
antipsychotic?
Yes, thank you. I was about to say, actually, antimalarial is what came to my mind, which is not great, but yes, antipsychotic. And so when I went back the next day, I got to see him do rounds. I went to see this patient, and the guy was completely different. One, he was apologizing to my dad for having been manic the day before, which was kind of interesting, which I think just points to the fact that he was regularly institutionalized, and so he knew he gets put in when he gets manic like that. He knows that he can be kind of unbearable, but once the antipsychotics kicked in, his personality changed quite drastically. And so as an approach, that's still the idea, is to do something to alter what's going on in the brain. Just doing it chemically can be reversible, not quite as drastic as a prefrontal lobotomy, but.
So that's what antipsychotic and antidepressants do, is the frontal.
Well, they're not so anatomically localized. Really what it is that there are neurotransmitter systems that project throughout the whole brain. Like serotonin and dopamine systems that are projecting through it. So an antidepressant is going to limit, or is going to act on the serotonin system. Antipsychotic is going to act on the dopamine system. And where that interacts with nuclei in the frontal lobes can have an impact on personality.
So is that why when somebody says like they were prescribed medication, they have bipolar, sometimes it makes it worse because it's not targeting the right?
Bipolar is actually an interesting situation.
Just the
And,
cocktail, what the mixture of drugs aren't correct for the person.
yeah, my dad, like I said, he's a psychiatrist. His specialty actually is in bipolar. And one of the things he did when he was in the state system was to look at how often people are misdiagnosed with bipolar and how the appropriate pharmaceuticals can actually help things quite a bit. A lot of people with extreme bipolar disorder will present looking like they're schizophrenic, and hearing voices and that kind of thing. And really, the right kind of drugs to approach the bipolar, which is the underlying cause, is better than the drugs for people that have hallucinations or whatever, which would be more like antipsychotic drugs.
But like some antidepressants I hear can make like bipolar worse.
If you're treating bipolar by treating the depression, you're actually not, according to my dad, treating it correctly. And so that can cause some problems. If you watch those drug commercials that are talking about, Abilify and whatever, or Prozac or whatever, it's kind of interesting in the side effect profiles that they have to say. A lot of the side effects are things that sound like what the drug's supposed to be treating. So like Prozac can increase suicidal thoughts or something like that, which you would associate with.
That's if it's giving to the wrong person.
But that's what I'm trying to say. That it's necessary, and this is what the psychiatrist really there to do, is to assess what's really going on, what's at the root of things. And just saying, hey, everybody gives out Prozac, let's give out Prozac to everybody that seems depressed, might be inappropriate. If the person's depressed because they're on a bipolar cycle, then the Prozac is probably not a good choice.
I'm gonna say, well, so it would be the Prozac that caused it, or it's just not the right medication for the bipolar?
Well, the person's already got some neurochemical issues going on, and taking that drug pushes the neurochemistry in a direction that makes certain symptoms worse, I'd imagine.
Probably just because one person committed suicide, they have whether it has a side effect.
Well, it's not just one person. There's significant statistical results showing that it does present that way for, it might be 5 or 7% of the population taking it or something like that.
And now, why do they usually say it's for young? Usually more in young adults than like the suicidal thoughts are usually.
Probably because the brain is still developing. And if you start messing with the neurochemistry with a teenager, you're going to affect some of the development of the brain. And that can actually cause other problems, which can
When
make
does
lots
the
of
brain stop?
about 20 or 25 years of age. So, and actually some of the parts that develop last are in the prefrontal area. Okay. I've been trying to find it. Several years ago when the data first came out, I saw the video. I didn't save it anywhere. And it's hard to find that on the internet anymore. But There's a study done looking at MRI images of brains from, I think it was 5 years of age up to 25 years of age. And with an MRI image, you can see the difference between gray matter and white matter very easily because of how MRI works. And what they found was that white matter develops postnatally. And so in an infant brain, there's not a whole lot of white matter. And it develops in a very particular fashion. And the last part of the white matter develop are the connections in the prefrontal lobe area. So that would suggest that, you know, a 15-year-old might make bad choices because their prefrontal cortex, which is in charge of making good choices, isn't wired up correctly. And before it becomes wired up correctly, the part of the brain that handles that is a deeper part of the brain, which is often thought of as a primitive part of the brain, which is really about, do I want to do that? Okay. So instead of should I do that, it's is that going to feel good? Okay. And so if you think about, you know, a toddler, they're not thinking long terms about things. They're saying, yes, I want a cookie now because it tastes good. It's not that I don't want a cookie now because I'm about to have dinner and I don't want to spoil my dinner or something like that. Okay. And so as people are getting into their late teenage years, that part of the brain is still developing.
So that's why something like schizophrenia doesn't start until teenage years.
Could be, yeah.
Because everything's fully developing at that point.
Yeah, it could be. Anyways, so I like getting off on tangents and answering questions that people are interested in, because if you're interested in something, you're going to learn about it. But it does sort of get us away from covering some stuff here. So I was talking about the frontal lobe, and that's sort of the motor part. And all of the rest of it is the sensory part of the cerebral cortex, in very broad strokes. Now, the precentral gyrus that's labeled there is the part of the brain that's responsible for causing muscle movement directly. The postcentral gyrus, which is the gyrus on the opposite side of the central sulcus, which is in the parietal lobe, is the part of the brain that receives information from your body in what we call somatosensation. Okay. Now, somatosensation is a sort of more formal term for what we usually think of as the sense of touch. Okay. But really, there's more to touch than just touch. There's pain, temperature, pressure, tickle, vibration. There's a few others there that I'm not getting. So all of that's what we consider touch, as well as just the sensory information about the movement and position of our body in space. So as I'm moving my arm like this, I know that that's happening because I can feel the joints moving, I can feel the muscles contracting and stretching and extending and all that sort of thing. That information goes to the postcentral gyrus also. So we get information about what's going on in our brain. Now, the precentral and postcentral gyrus are right next to each other. Okay. A neuron that tells a muscle to move, so the neuron that's telling the muscles to move my arm like this, might be located right in this area here. And then a neuron that's receiving information that I'm moving that part of my body is right here. Okay. They're actually right next to each other. Okay. One's on the motor side, the other's on the sensory side of things. Okay. So when we talk about the parietal lobe, because it contains the postcentral gyrus, which was our somatosensory cortex, we usually associate that sense of touch, somatosensation, with the parietal lobe. Okay. And then the occipital lobe back here is associated with vision. The first part of your cerebral cortex that processes visual information is found right here at the back tip of the brain. Okay. When I was talking about the eye cups earlier, I said that they connect to the diencephalon, to the thalamus and the hypothalamus. What the thalamus then does is it connects to the cerebral cortex, and in fact to the occipital lobe. And that's where you start processing your conscious perception of vision. Okay. And in the temporal lobe, some sources will talk about, and this isn't entirely incorrect, that it's associated with the sense of hearing. But really, the only part of the temporal lobe that deals with hearing is right here at the edge of the lateral sulcus. Okay. More importantly, in the temporal lobe, and the function I want you to associate with it more on the whole, is memory. Okay. Now, memory is really a sensory function. When you remember something, you remember how something smelled or looked or sounded or felt. Okay. You don't remember the motor functions associated with something. You remember your experience of that the feedback from your body of walking or moving or sitting down or whatever. So memory is really a sensory function, which is in the temporal lobe. I have another story that I want to talk about, sort of building off of our earlier thing there with, I can't remember the guy's name now, Joe? Is that his name?
Yes.
Yeah. Where he had the corpus callosum split because of intractable epilepsy. There's another story of a guy who had epilepsy that started here at the most anterior tips of the temporal lobe on both sides. So he had surgery to remove that part of his brain. And that's where the epilepsy started. So if they surgically removed that, he wouldn't have epilepsy anymore. And so they went in there and they removed the medial temporal lobe on both sides. Okay, so here's a temporal lobe. The medial side of the temporal lobe is right here. So they went in and cut out this part of the temporal lobe on both sides. This guy's famous because he's the only person that's ever had that procedure performed. And the reason he's the only guy that's ever had that procedure performed is that it was a really bad idea. People since then have had medial temporal lobectomies performed, but only on one side and not the other. Because having both sides removed caused him to lose his memory. Okay. Well, I should say that differently. Caused him to lose the ability to form new memories. Okay. He remembered everything leading up to the surgery, but everything after the surgery, he can't remember. I have in the video part, a little video that I found about the depiction of amnesia in movies. And I put this in here because it's kind of a neat little treatment of this idea I want to talk about. So the patient that had this bilateral temporal lobectomy performed is referred to as patient HM. Yeah, patient HM. He's since passed away, so he doesn't have to be referred to by his initials anymore, but I've never committed his actual name to memory. I just still refer to him as patient HM. But from that, what we discovered is that the temporal medial lobe is the medial temporal lobe is very important for memory function. Besides the cortex that's on the outside surface, there's a structure underneath, a nucleus deep inside called the hippocampus, which is crucial for memory function. Okay. Having both of those removed, he lost his ability to form new memories. Now, I'm mentioning the amnesia in movies thing because I want to illustrate this actually by referring to a few movies. They are not actually referred to in this book, in this video. Maybe one of them is, but not all three of them. Obviously, there's something about Finding Nemo here because Dory has some memory issues. And I don't know what's come of it, but I remember there was an announcement a year or so ago by Ellen that they're making a Dory-centered sequel to this. So hopefully we'll see more about Dory and her bad memory. But really what I want to talk about are three movies that have to do with memory loss. You might not have seen all three of them, and I'm not going to recommend that you necessarily see all three of them, because we go from really bad representation of memory to really good representation of memory loss. So the first one, which I hope you haven't seen, and I don't suggest you go see it, is a movie called Clean Slate. It starred Dana Carvey, whose only real lasting claim to fame is he's Garth in Wayne's World, and he's the church lady from SNL. But like many people from Saturday Night Live, he went on to pursue an acting career in movies, and one of the bad choices he made was this movie, Blank Slate. It was essentially supposed to be like a film noir murder mystery, sort of dark, seedy underbelly of LA, trying to find out who murdered somebody. But the memory aspect of it was that he played a person with amnesia, kind of like what patient HM would have. The problem with it, with the movie, is that they didn't do a very good job of really considering real science and what was going on. Now you can say that movies don't have to pay attention to science if they want to do whatever they want to. That's fine. But there's some really big problems with this movie. First off, there's the common trope of memory loss movies, which we'll actually see again in another movie that I'm going to say is a little bit better. But the idea that you only remember things during the day. When you go to sleep, you forget. That is not at all true.
That's not true.
No. But it works really well for movies, because they want to have action that takes place over the course of the day, and then when he wakes up in the morning, he has to kind of figure out who he is again. What really happens when somebody has amnesia like this is they can remember things for about 10 minutes, and then they forget things. Okay. And in another movie, I'll address that a little bit better. The other big problem they have with this movie, which is probably the worst thing that any movie can make scientifically, the biggest error any movie can make scientifically, which is to try to explain things too much. So the writer for this movie apparently went on whatever passed for the internet back when it was written to find explanations of this kind of memory loss. And they came across what was called Korsakoff syndrome. Korsakoff syndrome presents exactly like the patient I'm talking about. They, from the onset of the disease, they're not able to form any long-term memories for a while. Anatomically, the reason's a little bit different. It's not the medial temporal lobe, it's actually things that are connected to the medial temporal lobe. But still, the reason it's a big problem is Korsakoff's syndrome is experienced by severe alcoholics. When you get to the point that you drink instead of eat, so you're not getting nutrition into your system appropriately. Sorry?
That's my whole family.
Well, they're about to suffer from Korsakoff.
That's why I remember it as Smirnoff.
I've not heard that reference.
I remember that from 8 years ago.
There you go. Korsakoff syndrome. Not eating food, not getting nutrients is going to compromise tissue in the body in general sense. In the nervous system, there are structures that are actually on the outside surface of the brain, not anything we can see, or actually on the ventral surface, that start to die off because of the nutritional deficits that come with exclusively drinking alcohol over all other types of intake. And from that, memory loss is one of the first symptoms that set in. But within about 5 years, other symptoms set in which lead to death. So somebody with Korsakoff syndrome, one, is an alcoholic, a raging alcoholic, and two, has a limited lifespan where dementia is going to take over and they're going to pass away. In the movie, the main character, played by Dana Carvey, who was supposed to have Korsakoff syndrome, was not alcoholic, and of course at the end of the movie he got his memory back, which would not happen with Korsakoff syndrome. So the biggest sin of this movie is trying to come up with something sounding scientific to explain what's going on. And they did a horrible job of it. And I do not suggest that you go see Blank Slate. The next movie I want to talk about, you might very well have seen, especially if you laughed about my medulla oblongata earlier, which is 50 First Dates. This has that same trope, that she's lost her ability to form new memories. If you haven't seen this Adam Sandler movie, Drew Barrymore plays a woman with amnesia who Adam Sandler meets, falls in love with, and has to every day fall in love with her again, or she has to fall in love with him. So they go on a bunch of first dates, because that's all that she can remember. Anyways, so it's the same trope. She can remember things during the day, and when she wakes up in the morning, she forgets everything that happened before, and she thinks it's the day before she lost her memory, which is actually part of the plot point. That is still the same kind of egregious mistake of the previous movie, but it's forgivable for two reasons. One, I like Drew Barrymore and Adam Sandler, but two, there's a character in that movie that's a nod to, we understand the science, but it doesn't work in the movie that well. There's a character called 10-Second Tom. So if you've seen the movie, you know this guy. They go to a mental institution where Drew Barrymore's character checks in every so often when she's having issues with her condition. And one character there's 10-Second Tom. And so he's being introduced to a series of characters in a row. And at the end of that, he goes back to the first person and says, "Hi, I'm Tom. I don't think we met." Because 10 seconds has passed. He doesn't remember. Now, more scientifically accurately, it would be 10-minute Tom. That's how long people can remember things. But it would make a horrible joke in a movie for it to be 10-minute Tom. Because it'd have to play out for 10 minutes and then go back and say he doesn't remember something. So the 10-second thing is so that it works better as a movie joke. But the fact that it's 10 is actually a nod to the fact that they understand how memory really works, so they put that in there. And that whole Hollywood trope of, waking up the next morning and forget everything is obviously false. The other thing that's good about that movie is they don't try to explain it. The only explanation for why she lost her memory is that she was in a car accident and she hit her head. And the medial temporal lobe, right here, is sitting in the skull, and it's covered by the greater wings of the sphenoid bone. If you hit your head, it's entirely believable that the medial temporal lobe part of the brain will be driven into the sphenoid bone a little bit and potentially cause some trauma there, which would result in this kind of condition. They don't try to explain too much other than say that she was in an accident, she hit her head. And that's a fair explanation. So actually some things about that movie that are similar to the really bad movie, but the fact that they do better with the science makes me like it more. The third movie I want to talk about is Memento, which you may or may not have watched. If you haven't watched it, I'd like to strongly suggest that you do, with the caveat that it can really mess you up. Okay? So if you're not into weird kind of experimental movies, don't try it. It's made by Christopher Nolan, who's the guy that did the Batman trilogy. Okay? It was written by Jonathan Nolan, who is his brother, who wrote Interstellar. Okay? And I think Christopher Nolan had something to do with making Interstellar too. But the script for Interstellar is at least partly Jonathan Nolan's work. So these are really good filmmakers, really successful filmmakers. What Memento is about, again, it's a murder mystery, kind of that seedy underbelly LA kind of thing, sort of like Blank Slate, but done a lot better. So the main character, who's played by Guy Pearce, I think it is, who I can't remember offhand what else he's been in, but you'd recognize him if you saw him. He's lost his memory. He can only remember things for 10 minutes, like it's supposed to be done. So in the movie, it's told from his point of view, and you don't know what just happened 10 minutes before, just like he doesn't. Okay? So the movie's told in reverse order. The first scene in the movie is the last bit of the story. So you see the last thing, and then you jump back in time 10 minutes to see what happened just before that. And then you jump back in time to see what just happened just before that. So you're experiencing it kind of like the main character. He doesn't know what just happened. So you don't know what just happened leading up to the scene that you're watching. Of course, you remember what happened in the movie. It's kind of I don't want to use an inappropriate term here, a mind play, we'll go with that one. If you can't really get into that kind of movie, you probably won't enjoy it very much. But it's really neat because it does actually show his experience in terms of the fact that he can't remember things that happened just 10 minutes before. There's a great sequence in the movie where it cuts to, he's standing in a parking lot between some cars, and the first thing is the voiceover is thoughts. And he goes, "What's going on?" Because he doesn't remember what just happened. And then suddenly there's gunfire. He's like, "Oh yeah." And he starts running so he doesn't get shot. And then when you cut back, you find what leads up to him being chased through this parking lot by somebody with a gun. But you didn't know it was leading up to that, so it's kind of a surprise to you as to the character that he's being shot at. It's a really well done take on what having that kind of an amnesia is really like. And then also they do a pretty good job of not trying to explain it. Now, part of not trying to explain it comes from the fact that the narrator is this guy that's lost his memory. So he doesn't remember how he lost his memory. Instead, he has these kind of fragmentary flashbacks occasionally that suggests he might have hit his head. So part of what's going on is trying to figure out who killed his wife. And as far as he knows, there was a break-in at his house. He was assaulted, and he hit his head probably on the corner of the bathroom sink, which would be the same thing as Drew Barrymore. So there could have certainly been bilateral trauma to the medial temporal lobes. But he's not sure of that. And actually, one of the interesting things, one of the mind play parts of the movie is really understanding what happened, because there's an alternate theory suggested by the movie if you're paying close attention to why he actually has this problem. But I'm not going to give that away. You got to watch the movie if you're interested. So those are some movies that get at the kind of amnesia that would come from a medial temporal lobectomy. This patient HM that I mentioned had that performed back in the 50s, like 53 or something like that. He couldn't remember anything from that point on, but neuroscientists like Gazzaniga, not Gazzaniga himself, but those kind of people would study memory by asking him to perform tasks. So they'd ask him to, memorize a telephone number, and then they'd ask him after certain intervals if he could remember that telephone number. And from that, they kind of just figured out that people can remember things for about 10 minutes. Maybe 15 minutes if you can rehearse the information. So if somebody tells you there's a phone number and you repeat it to yourself over and over again, as long as you're practicing that, you can remember it. Okay. And if you practice it for a little while, you can probably retain that memory for about 15 minutes. Of course, nowadays, nobody gives you their phone number. They just put it in your phone.
That's why you forget something when you go into another room.
Right. So that kind of thing. You might have thought, oh, I need to go into the living room to get, my phone charger or something like that. And as you're going there, you realize that you need to take the laundry downstairs and you need to feed the cat and all that sort of thing. By the time you get there, no, not 10 minutes later, you remember. What it is you've distracted yourself and you've forgotten what it is, and you never formed the long-term memory of why you need to go there in the first place. So rehearsal is the point.
Okay, so just keep thinking about the phone charger.
Yeah. And not get distracted by everything else. Anyways, so like I was saying, patient HM had this done in about the 53 or 57. I can't remember the date exactly. But researchers would come and ask him if he remembered things. One type of memory is, remembering events. And so every generation has an event that everybody remembers, like where were you on 9/11, that kind of thing. So he was asked repeatedly by researchers, did you know about somebody who was assassinated or something like that? Okay, and this would be Kennedy's assassination in '63, which was not too long after he had the surgery. Eventually, when he was asked that question, he said, yeah, somebody important got shot. Okay, he couldn't remember it happening. He doesn't remember the event itself, but the question was asked so many times by researchers, he started to form a memory of sorts of it. Just not a very strong memory, but there is some chance over the course of decades that central nervous system tissue might be able to start repairing itself, which I talked about that with you guys before, right? Because you were asking Amanda about some injury. So there's more evidence that long enough time, much longer than your average human lifespan, there might be repair of central nervous system tissue, just not in a timely fashion for most people to make use of. Okay. Now, in the next part of the book down here, it talks about more specific structures within the cerebral cortex. And this picture, it comes from the work performed by, I thought there was a title for this, but Brodmann. He was I believe, German microanatomist, which meant that he liked making microscope slides of tissue and looking at the structure of the tissue within that. And so what he did was he took sections of tissue throughout the entire cerebrum and looked at the structure of the neurons and the white matter and other things in each microscope slide, and anatomically determined that there were, I think, 52 different regions of the brain or something like that, which are called Brodmann's areas. It was strictly an anatomical study, but nowadays we refer to these particular areas, which are highlighted by different patterns in his stippling, as, you know, areas 1, 2, 3, 4, et cetera, that correspond to functional different areas in the brain. So for example, back here, this area, which I had the artist highlight in this, you know, kind of flesh color or whatever, this is Brodmann's area 17. This is the primary visual cortex. So on the lateral surface of the brain, you just see this little very, very back part of the occipital cortex. But really it runs along the occipital cortex medially up to that parietal occipital sulcus I pointed out there. This is the part of the brain that's getting information most directly from the retina. It actually isn't getting it from the retina, it's getting it from the retina through the thalamus. But this is where you start processing information. It then spreads out into area 18 and area 19, which is kind of the rest of the occipital cortex. And then it's going to spread into these areas up here in this parietal cortex, or these areas down here in the temporal cortex, as we process more and more information about vision. I don't want to go into that story tonight for two reasons. One, we're running out of time, and you've seen how I can tell stories tonight. But also because I go into that a bit in the book. Okay, so between this week and next week, look into my explanation of the visual processing between the occipital, parietal, and temporal lobes there, and especially what's talking about the ventral and dorsal streams or pathways or whatever I call them, which is sort of how we process visual information up here and down here. It mostly has to do with the dorsal stream going up into the parietal cortex is about where things are located. And the ventral stream going down into the temporal lobe is what we're looking at. And that corresponds to the memory function, because visual memories, what things are processed down here largely. Okay. I mentioned the auditory area that's located right here, which is often associated with the whole temporal lobe, but really it's just that area right there. On the left side of the brain, which is what we're looking at in this picture, this is the lateral view of the left side of the brain. This area up here, colored sort of brown and tan, called Broca's area, and this area back here around the purple pink shades called Wernicke's area. Those are the two most important areas for language function. And I want to continue on and talk about that in more depth, which I'm going to save for next week, which will fit into some of the clinical things that we have to talk about. Now, I only have about 10 minutes left, and I do want to take a little bit of time to go into the peripheral nervous system section. What's in here that's relevant outside of what we've already talked about, the ganglia nerves, and we looked at this stuff under the microscope earlier. Within the nerve section, aside from the basic structure of nerves, are the cranial nerves. And this is showing you on the ventral side of the brain where the different nerves are. There are 12 pairs of nerves called cranial nerve 1 through cranial nerve 12, which is noted by Roman numerals. So cranial nerve 1, cranial nerve 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, going through, are laid out there. On the brain model that you have in front of you, on the labeled half, there will be Roman numerals pointing to where these connect to the brain themselves. Like I said, what I used to do with this material in lab is I'd go through this in some detail. And what I did going through that in detail was basically explaining this table in some depth. But now that I have the book, I've just put the table in the book. There's actually a couple of mistakes in the table. So on Blackboard, in the current week folder, which is the nervous system thing, there's a link in here that says Cranial Nerve Study Guide, which is that same table. Oh, I thought it opened up in another window, but instead it has to download it. So it downloads a Word file, I think. Which is that table. And I just want to point out where a couple of corrections were made. Oh, so actually there's two tables here, and this table is relevant next week. But this is a table that's in the book there. In the fifth row, which is the cranial nerve 5, the trigeminal nerve, in this last box here, the word trigeminal is the only word that's in the book. There's more here explaining what's going on there, which got left off in the book version here. So where it just says trigeminal here, there's more to that, what's supposed to be in that box. And you can see it in that Word file that I have here. And I thought there was another change, another issue. Oh, I guess I didn't. I was working on updating this, and there are some nerves that are responsible for both sensory and motor function, which are designated by a B here. And so it says sensory and motor of the face, or motor and sensory of the viscera, et cetera. Or motor of the throat and taste, which is a sense, that kind of thing. I have a version of this, which I haven't posted online, which splits these rows up into two sub-rows, one for sensory and one for motor. But I think I got a little too busy that way, so I didn't include that here. But this mistake here is a big one. And so what I have in the Word file completes the rest of what's supposed to be in there. Now, the way that I've laid out this table, which is in the book too, the first column is a mnemonic, a way for you to remember the specific nerves' names. So the mnemonic is on old Olympus towering tops, a Finn and German viewed some hops. It's a rhyming couplet. Out in the hallway, there's a little display, I think, across from the, it's either across from the elevators or across from the doors next to the elevators, where a student put up some information about cranial nerves, and they have that same mnemonic there. There are other mnemonics which are sort of more appropriate because A and corresponds with the word auditory, but that nerve is actually called the vestibular cochlear nerve. And the reason why it's not called the auditory nerve is that it does more than just auditory or hearing function. So this is the more complete name, which has only been adopted formally in the past 20 years or so. And this is a fairly old mnemonic. Also, the 11th word, some, that starts with S, stands for spinal accessory. And a lot of sources will just call this the accessory nerve. They just leave off the word spinal. I didn't leave it off here because I think it's important to understand that it's the spinal accessory nerve in what it does. It helps spinal nerves do their job. If you go on to Wikipedia and you search for a page about cranial nerve mnemonics. You'll get a page that has like 24 different mnemonics. They come in two different sorts. Either it's this mnemonic or a variation of this, or it's another mnemonic that starts with OOO. Okay, I don't like that mnemonic because instead of having OH, OH, OH is the first three words, there are three different words here that correspond with three different nerve names. But the other one, OOO, it's really hard to come up with a mnemonic sentence that has three O words in a row. So the more modern versions just have the word OH for all three of them, which I don't think is a very good way to do it. They're based on what I consider the dirty version of the mnemonic. And I do not know that mnemonic by heart. I've purposely not learned it so I don't accidentally say it in class. But it starts off with OOO, okay, which can have several connotations to it. But also, there's a word there that starts with a V and a word there that starts with an H. And I'm not going to tell you the V word, but the H word is hymen. So you can kind of guess where it's going. Okay, it's the dirty mnemonic. Now, mnemonics are used often by medical students, especially to help them remember things. And apparently sex really helps remember things. There's another mnemonic, which I think I explain in the book, getting at the function. So some of these are sensory nerves, like the one for smell or vision or for hearing and balance. Some of them are motor nerves, like for moving the eyes or moving the head and neck or the tongue. And some of them are both sensory and motor, such as 5, 7, 9, and 10. So if we use S for sensory, M for motor, and B for both, we can have a mnemonic for that too. The mnemonic I use is some say marry money, but my brother says brains, beauty matter more. Okay, it's 12 words. All of them start with S, M, or B. The first, second, and eighth ones start with S. The 5th, 7th, 9th, and 10th ones start with B, and all the others start with M, okay, which would be what? 4, 5, 6, 11, and 12. There's a dirty version of that, which is on the wall out there, which really upsets me. But whoever was in charge of the student that made the cranial nerves display up there didn't apparently make any editorial decisions about what got put up on the wall. But it is, some say marry money, but my brother says something, something matters more. And that something, something are two words that start with a B. The first one is big. Okay, you can figure out what the second one is probably. If you don't have enough imagination to figure out what that second B word is, it's on the wall out there. But I changed it to brains, beauty, because I thought it was a little bit more appropriate way to do that. And I did consciously decide to put brains before beauty in my version of the mnemonic. But anyways, those mnemonics will help you remember either the name of the nerve or its general function. Now we're to the end of the night. I do have some other things to say about the cranial nerves. I'll continue that next week. There is a lab quiz. If you want to try the lab quiz this week, feel free. You do get 3 attempts on the lab quiz. So if you take it once and you don't do very well, you might want to hold off till later on. Most of the information that I would say is in the book anyway. So if you read the book section about the cranial nerves, I think you'll be prepared for the quiz as much as possible. But if not, you can wait till next week. It's set right now to be due before next week, but if you do it late because you're waiting for next week's information, that's fine, because it doesn't impact any other assignments. Otherwise, have a nice night. We'll continue on with some of this information, looking at the surface of the brain and getting to know a little bit more about what we're seeing, and also thinking about function a bit more in terms of clinical neurological deficits, which will be another way to think about this. So thank you. Have a good night.